So here we'd now like to do problems 2 and 3 on quiz 3. And so in problem 2, we want to find the electric field at radii less than capital R, which is now inside the sphere here. So I'll draw my Gaussian surface at my location inside the sphere at some radius little r. And so the only charge that's being enclosed, if I have a sphere that has charge on the inside and charge on the surface, is the charge on the inside. So when I go to compute Q enclosed, I'm going to need to integrate the rho d tau. So my charge enclosed in this situation would be the integral, I have to do a triple integral, 2 alpha over r, d tau. D tau in spherical coordinates is r squared sine theta dr d theta d phi. And so the r integral, I'm going to run from 0 to r because I only want to enclose the charge out to my Gaussian surface. The theta integral runs 0 to pi, and the phi integral runs from 0 to 2 pi. And when I do the theta and phi integrals, I'm going to get a 4 pi. And I have a 2 alpha, which are constants that come out front. And so I see here that I have an r down bottom and an r squared up top. So I'm integrating r dr from 0 to r. So the charge enclosed as a function of r is 4 pi alpha. When I integrate r dr, I'm going to get a 1/2, which is going to kill this factor 2 that I have left out here. And I'm going to get r squared. So the integral of r dr is r squared over 2. Evaluated from 0 to r is just going to be r squared when I cancel out that 2 that's out front. So that's my charge that's enclosed. And so if I go back here to Gauss's law, the integral of E dot dA is Q enclosed over epsilon naught. Well, the left-hand side, I will say the magic words that the electric field, there's spherical symmetry, and the electric field is constant along the surface of the sphere. And so the surface area of my Gaussian sphere is 4 pi r squared because I'm, again, using this blue Gaussian surface at a radius of little r, not the big R. And so that's my, my flux integral. And on the other side, I need to use Q enclosed over epsilon naught, and I just found Q enclosed. I found that Q enclosed is 4 pi alpha r squared, and I divide by epsilon naught. And I see here that the 4's cancel out, the pi's cancel out, and the r squareds cancel out. So for this charge distribution, the electric field is constant inside the sphere. So there is my answer to problem number 2, that the electric field points radially and it has a constant value inside the sphere. So now the difference between problem 2 and problem 3 is now I'm moving my Gaussian surface outside the entire sphere. So again, I'm going to have the integral of E dot dA is Q enclosed over epsilon naught, and on this side, of course, I'm going to have E times 4 pi r squared because I have a symmetric situation here. But now, in order to compute Q enclosed, I'm going to have 2 contributions. I'm going to have the charge from the interior, and I'm going to have the charge from the surface. The charge from the interior is integrating the rho, and the charge on the surface is integrating the sigma. Now, for the rho integral, again, I'm going to have 4 pi when I do the theta and phi integrals. And the rho was 2 alpha over r. The sigma was just minus alpha. So, just from what we had before, the only difference in the integration of the rho, see up here we had the integration of the rho, we had the 4 pi times the 2 alpha integral of r dr, but we only ran out to, on the inside, this little r, which is my Gaussian surface inside the sphere. Once I'm on a Gaussian surface that's outside the sphere, I'm going to stop this integral at capital R. So that's my amount that I would have here due to the interior. So the amount that I would have due to the interior is going to work out to be 4 pi alpha capital R squared. Now, for the surface charge density, I have constant surface charge density. If I have constant surface charge density, then the charge is equal to the surface charge density times the surface area, right? It's because sigma is Q over area, and if sigma is constant, then I simply get to multiply the sigma value by the surface area. Okay, well, the sigma value was minus alpha, and the surface area of a sphere of radius capital R is 4 pi capital R squared. And I see now that when I add up the charge on the interior and the charge on the surface, I get 0, because the charge on the surface is the negative of the charge that's on the interior. The problem was picked to be this way. And so when I go to integrate the integral of E dot dA and set that equal to Q enclosed over epsilon naught, well, over here I've got 0 because I don't have any charge enclosed, and here I have E times 4 pi R squared. So that tells me that my electric field is 0 at any position outside the sphere. And that is my answer to problem number 3.